Hello, everybody. My name is Alex Vaughn. I'm a master's student in Duke's Mechanical Engineering program, and in this video, I will be presenting an overview of my master's project. My advisor was Dr. Earl Dowell, and the topic was on a Rayleigh-Ritz approach to beam stiffened plates. Firstly, I want to talk about this project's background and motivation. In the field of aeroelasticity, there's a phenomenon known as panel flutter. Panel flutter is a self-excited instability that can occur on the skin panels of supersonic aircraft. It appears as large vibrations of the panel and is caused by the coupling of the structural dynamics of the plates with the high-speed aerodynamics. One way that aircraft designers mitigate panel flutter is they add beam stiffeners that run across the plate to stiffen the plate and raise the natural frequencies, which typically delays flutter to a higher speed. Figure 1 provides a schematic of a beam stiffened plate in this aerodynamic condition. In order to predict at what speeds panel flutter will occur with a beam stiffened plate, it's necessary to know the natural frequencies and the mode shapes of the beam plate system. FEA may be a first approach, but FEA has its disadvantages, especially if you need to cycle through many different beam configurations for the optimal solution. In this presentation, I present a different approach using the Rayleigh-Ritz method. The Rayleigh-Ritz method has two main advantages. One, it is less computationally expensive than FEA, and two, whereas most FEA codes are a black box, this Rayleigh-Ritz method provides analytic expressions for the natural frequencies and mode shapes, which provides insight into how system parameters affect these outputs. I now want to talk about the structural dynamics model. We start out in typical Rayleigh-Ritz fashion by assuming that the deflection of the beam, WB, and the deflection of the plate, WP, can be represented in a modal expansion, where psi represents the mode shape of the component by itself, and Q represents the generalized coordinate, or weighting factor. We will then couple the system by stating that the deflection of the beam and the plate at points xs, yc must be equal to each other. For a true beam stiffened plate, the number of constraints of this form is infinite. The beam is rigidly attached to the plate everywhere along its span. However, we have to approximate this by attaching the beam to the plate at finitely, in this case s, many points. Once we have all of our constraint equations, we take them, as well as the modal expansions, and plug them into Lagrange's equations to get the equation of motion of the coupled system. Lagrange's equations yields a square matrix, whose size is equal to the number of constraint equations. The matrix element at a row F, column G, looks like this, where psi b represents the mode shapes of the beam, psi rx ri represents the mode shapes of the plate, m and n represents the generalized mass of the beam, m rx ry represents the generalized mass of the plate, omega b represents the natural frequencies of the beam uncoupled, and omega rx ry represents the natural frequencies of the plate uncoupled. To find the values of the natural frequencies of the beam plate system, we will need to take the determinant of this matrix and find its roots. Once we have the roots, which are the natural frequencies, we can plug them back into the matrix to find the mode-shaped eigenvectors of the coupled system. Now the question is, what does the determinant as a function of omega, the natural frequency, look like? It looks something like this. As you can see, it's a pretty unique looking function. These dashed lines here represent the asymptotes of the function that occur at all the natural frequencies of the individual beam and the individual plate. Again, the roots of this function, where it crosses zero, are the new natural frequencies. In practice, finding, say, the first 5 zeros of this function is quite difficult. The first reason is that there is no algorithm that can find all the roots of a general function. All algorithms, at least that I know of, will only converge to one root, given an initial guess or interval to look over. To still be able to find multiple roots, my code uses a method called monkey bisection. Monkey bisection is just like the bisection method, but instead it picks random subintervals to apply the bisection method of a given large interval. I call it monkey bisection because this random method of trying to find roots is similar to a monkey throwing darts at a dartboard. Because monkey bisection is a probabilistic method, if you have some interval of length L whose roots you care about, and you set each subinterval to be epsilon, to be 8% confident that the entire interval has been covered by bisection subintervals, this many bisection subintervals, or greater, is necessary. Monkey bisection works well most of the time, but in certain cases where the subinterval has grouped two roots together, it will only converge towards one. The second numerical challenge involves the fact that for stiff systems, so systems with many beam plate constraints or high stiffness moduli, the determinant function becomes incredibly flat and small. This can introduce numerical precision errors in finding the roots of the function, since the determinant function is almost always near 0 in the eyes of monkey bisection. To account for this, I have a sim-log or symmetric log transformation in my code. On the left here is an example determinant function. Notice that the function itself is almost always on the order of 10 to the negative 12th, or smaller, so it's difficult to find exactly where the zeros are. After taking a sim-log transformation of the function, it looks something like this. It has been stretched about 0, and now the function is closer to the order of 1, and the zeros are much easier for monkey bisection to find. For reference, here's the expression of the sim-log transform. I now want to talk about some of the numerical results of this model. The simplest boundary condition is where the plate is pinned on all sides, as well as the beam on its ends. When you non-dimensionalize the determinant function with pinned boundary conditions, it turns out that the natural frequencies, and thus the mode shapes, depend only on 3 non-dimensional groups: what I've called the system number, the aspect ratio, and what I've called the mass number. The system number depends on the elastic modulus of the beam, the moment of area of the beam, the mass per unit area of the plate, the flexural rigidity of the plate, and the mass per unit length of the beam. The aspect ratio only depends on the ratio of the 2 lengths of the 2 sides of the plate. Finally, the mass number depends on the mass per unit length of the beam, the mass per unit length of the plate, and the length of one of the sides of the plate. So again, the natural frequencies of the system and the mode shapes depend on these 3 parameters, as well as the position of the beam with respect to the plate. Out of these 4 plots, I would only like to talk about one to save time. Here, I have a plot showing, for a sample system, the non-dimensional frequency of the system's first 3 modes with respect to beam position. By beam position, I mean where along the length of the plate is the beam located. As we can see, for the first and third natural frequencies, the maximum frequency occurs when the beam is located halfway across the plate's span. This makes sense because without the beam, the plate's natural modes have a maximum displacement here. So when we add the beam, the displacement of the plate decreases a lot, and the strain energy increases a lot, so the natural frequencies increase a lot. For mode 2, we see that the relationship is even more complicated. It has a minimum where mode 1 and 3 had a maximum. This is because mode 2 of the plate has a nodal line, so the displacement of the plate is already close to 0 when we add the beam to this location. We aren't stiffening the system at all, we're only adding mass, so the frequency is low. These 2 peaks on either side occur because we are adding the beam to areas of high displacement of the second mode shape. Notice that the beam can be placed in such a way that the original second mode shape has a higher frequency than the original third mode shape. The last plot that I want to look at is a plot of the system number. Here, for the pin case, I varied the system number while keeping the mass number and the aspect ratio constant. As we can see, for the first 3 modes, the natural frequencies exhibit interesting behavior. For low system numbers, the natural frequencies of the beam plate system are actually lower than the natural frequencies of the plate alone. I've marked the first 3 natural frequencies of the plate along these red, purple, and maroon lines. This happens because for very low system numbers, the effective stiffness of the beam is very low. It doesn't stiffen the system much, but it does add a bunch of mass, which drops the frequencies. For particularly high system numbers, we see that the natural frequencies of the system converge, and no further increase of the system number yields any appreciable increase in natural frequencies. So this is to say that there is a limit of how much you can raise the natural frequencies of a beam plate system. At high system numbers, the mode shapes of the beam plate system look like mode shapes of the plate alone, but at a higher modal index. Here are contour plots of the first 3 mode shapes of the plate alone on the left. On the right is the first 3 mode shapes of the beam plate system. The orange line indicates where the beam was added, and the black dots indicate the constraint points. As you can see, the first mode shape of the beam plate system looks like the second mode of the plate alone, like I mentioned. This is true for modes 2 and 3 of the system. They look like higher order modes of the plate, since we have artificially added a nodal line. I would like to conclude by highlighting some of the lessons that have been learned from this model. Firstly, runtime is influenced heavily by the number of constraint points. This is because the size of the matrix, and thus the complexity of the determinant, is dependent on this parameter. Also, one should avoid placing constraint points on nodal lines of the plate modes, as well as using aspect ratios that are rational. This will cause numerical issues because sometimes degenerate modes, or modes that have the same natural frequency but different mode shapes, can occur for plates. Also, it is difficult to find zeros of the determinant function when the beam and plate have natural frequencies of similar order. In terms of future work and study, there is a lot that can be done. Firstly, aircraft designers are often concerned with weight saving. Can this method be used to optimize the beam dimensions and weight to induce certain natural frequencies for the system? Also, experimental validation using modal impact testing to compare with the model is of interest. Finally, this model can be generalized to arbitrary beam position or angle, plate geometries, and multi-beam systems. Here, I provided the first mode shape of a more general condition of the pinned plate case where the beam is along the diagonal. Also, here is an equation that I have derived for the general case of multiple beams. Finding the roots of this characteristic polynomial posed by the equation will yield the natural frequencies and the mode shapes of any general system.